really cool about this is you can scroll in, and the reason I've scrolled out is I've got to scroll out for a bigger reason right now. We'll scroll back in. But what's really, really cool is not only does it have the planets in the solar system, it's also got any of our satellites or any of our exploratory space information. And you can actually see there's Voyager 1 right there, and Voyager's about to, one of the Voyagers are about to, one of them's left the solar system already. But you've got all of the various pieces of what we know. You've got the couple of comets in here. And you can actually come in a little closer and closer and closer. But I want to point out Jupiter before we go in a little closer, because Jupiter's doing something really interesting right now. And it relates today to part of the lecture, which is one of the reasons why I do this. And as we come in a little further, we're about to experience it with Mars again. We will experience it, and if you come back way out, Jupiter's one of them, but Saturn's another one. Yeah, Saturn's another one, and we haven't quite gotten there on Saturn yet. And then I think it's Neptune is the other one. Yeah, Neptune, we haven't quite got there yet either. So look where we are in relationship to, so Earth is right here, and look where we are. When we're looking out in the night sky to Jupiter, when we're looking out in the night sky to Saturn, and when we're looking out in the night sky towards Neptune. And it's, we're about to be doing, and even though this is astronomy and not astrology, if you look up the phenomena that we're about to have, you're going to see a lot of astrology stuff. It's kind of entertaining right now, but you will get that. But this is the NASA site. It's kind of fun to play with because you can also rotate it around. You can look from the underside. But one of the other things I want to show you, and I'm going to kind of put it in here, and we're actually going to scroll in because we'll talk a little bit about why Pluto got demoted. And you can actually see the orbit of Pluto is not in what they call the plane that all the planets are in. You can actually, if we go into Neptune, and we'll look at Neptune and Saturn here as well, but we essentially are out on a plane around the equator of the sun. And if you go back and you look at the planets, let's look at Saturn real quick. Saturn, of course, it has its rings, and we are actually on a ring very much like what the, around the sun, like what is going around Saturn. And if we go to Uranus, Uranus is also one, no, it's the other one, it's Neptune. They don't have it? They're not showing it? Dadgummit. One of the other planets also has rings, but it's cockeyed. It's been hit by something, and it's cockeyed. But you can go out there and look at it. The reason I bring this up is because you guys do have a link in Blackboard associated with it, but the evening of September 12th, Jupiter completed it completes its retrograde loop. So Jupiter just completed that, but we're about to have, as you start scrolling through and looking at what's happening in the night sky, you're going to see that Saturn is going to do it. Saturn's it's going to look like it stands still in the middle of the night on September the 29th, and it's going to complete part of its retrograde loop And then you'll start to see the one for Neptune kind of come in as well. And as well as Mars. And Mars really, the big part of Mars's was done last June. But we're going to talk a little bit about retrograde. So if you go back over into, and a lot of you got pinged this morning, I'm sure, your phones blew up and all of that. In this week's solutions and example videos, you have the video about the falling objects. You got a video about perceiving acceleration. I gave you a couple of tutorials on Newton's laws that you can look at. I've added what is a force. We're going to go here in just a minute, and we're going to talk about Kepler, and we'll actually go ahead and click on this, Kepler's laws. So you've got that in here. Looking back at Kepler's laws, so you've got that part. Let's go back. So if you're bored this weekend, there's all kinds of cool stuff to watch. This is a BBC documentary on Newton, how Newton developed his laws. I got a couple of sample homework problems in here. These are the National Science Foundation puts out videos using sports and looks at Newton's laws. I've got another Veritasium about weight. This one is about inertia, why does things keep spinning? And this one looks at the explanation of retrograde. And then we've got Kepler's laws of planetary motion, and then the article for the night sky. And if you haven't really looked at it or really done anything with apps on your phone, I think I have my phone out here. And I'll show you the app that I'm currently using. My daughter and I actually went and did several different apps on phones to look at which one we thought was going to be the best. I'm actually using Star Tracker. Of course, I have an Android phone. We'll give it a second here. I'm using Star Tracker, and when you open up Star Tracker, right now it's a white screen, it will give you, and you can move it around, and you can actually find what you're looking at in terms of where it is. One of the things I do like about it is it does give you the outline of the various constellations. So, like if you want to do Scorpio, it kind of shows you the outline. It also points out some of the nebulas and things like that, so you can actually look at those things. So you've got lots of help, and you're probably all going, how does this relate to physics class? Well, this is very important to physics class, because this is actually what gives us Newton's law. So I'm going to go back to this real quick, because I want to show you what's really, really cool about the internet is if you click on Newton's papers, it's actually going to take you to the Cambridge Digital Library, and you can actually do and open Newton's documents and open the various documents that are there. And one of the things that Newton was doing, and we're about to actually dive into this, is here's the actual page where he starts trying to validate Kepler's laws. And all of his notes, except for his chemistry notes, are uploaded and online at the Cambridge Library. So as you guys start doing your laboratory notebooks, be aware that people will look at them down the road. You may think, oh, these are just strictly for my use. No, we actually go in and you can see people's notes, and you can go back in and you can actually look at each and every page that is still there from his. And if you scroll through this, We're about to actually talk about this diagram here in just a second. He's going through and he's doing his determinations, and you will ultimately see his hand calculations in here. People do go back and look at people's notebooks. And in fact, when I first jobbed with Phillips Petroleum, I was hired as a researcher from Phillips Petroleum, but my undergraduate research was dealt with the evolution of hydrogen at a cathode. So we were separating water into hydrogen and oxygen. That's exactly what we were doing. And about my first year when I got hired on was the stuff with cold fusion, if anybody ever remembers the cold fusion stuff, or has even heard of the cold fusion stuff. That happened my first year at my work. They wanted my undergraduate research notes because we were trying to figure out if cold fusion was really the case. And most of us who had worked in the hydrogen, evolution of hydrogen stuff said it was a bad hydrogen reaction. So my undergraduate research notes got passed around the research center of Phillips Petroleum because of work that I had done as an undergraduate. And we were trying to decide if Stanley and Pons and those guys actually had something or didn't. So you'd be amazed at where your research notes go. And we actually can look at Newton's papers to actually see those things. So kind of fun things to look at. And what's really cool is you can actually see how calculus gets evolved in through these papers, because what he's going to ultimately do is take smaller and smaller increments and do the calculation, and that's how we developed calculus, to look at the calculus of things. So it's kind of pretty cool to know that stuff that we look at and going in is out there. So if you want to go ahead and hit the lights, because now we're going to focus mostly on the document camera. Other fun asides, Kepler was actually hired because he was a very good calculator, human calculator. And what was happening in terms of the history, remember, physics was actually considered to be a philosophy as much as it was a science up until the early 1900s. In fact, we were philosophers, not scientists per se, until the early 1900s. But what was happening, there was a guy by the name of Brache, and I think it's spelled B-R-A-C-E. Interesting for all of you medical types, it's a case of was he poisoned or not? Because Brache goes to a party one night, comes home very, very ill, dies within 24 hours. And Kepler is actually accused of having poisoned him. But what is known is that Kepler actually stole a lot of Brache's notes. Whether it was legitimately stolen or the family, there's actually a lot of controversy as to whether or not Brache had actually given it to him or did Kepler steal his notes. But Kepler actually ends up with Brache's papers. Brache was a very, very good observer. Took incredible notes with regard to the motions of the planets in the night sky. This is also the same time frame that they're arguing, is the sun the center of the solar system or is Earth the center of the solar system? At this point, they've pretty much convinced themselves that the sun is the center of the solar system and that these observations of the planets are very, very important. So there's a lot of interesting discussion. Brache was very, very secretive, did not like to share his observations, but he knew he needed help with the calculations, which is why he hired Kepler. And then when Brache turns suddenly ill and dies, Kepler ends up with the notes, and he ends up publishing all the work, which is why we call them Kepler's laws. There's a really cool book that has just recently come out about the poisonings, and it's actually thought that Kepler didn't do the poisoning, that it was just there's a possibility, but if you also follow along that time period, there were lots of things that got added to wine that were to make the wine more palatable, like ethylene glycol, which is a poison, which could kill you. They drank out of lead containers, they used lead salt. Queen Elizabeth did not go, the first Queen Elizabeth did not go out because all of her makeup was lead-based. And so that's why she did not go out after a while. And she essentially contributed to her own illness because she was giving herself chronic lead poisoning. So, and even the medical treatments at the time, you might be as likely to be poisoned by taking your medicine as you were being poisoned on the other way. So it's a really cool book about poisoning that actually goes into the Kepler-Brockey story. But what Brockey had done is he had made observations, and we've got the good old sun here. And we've got Mercury, and we've got Venus, and we've got Earth, and we have Mars. And what's the other interesting thing about the orbits is we all end up orbiting in the same direction around the sun. Whether we're Mercury, Venus, Mars, or Earth, we actually rotate around the sun in the same direction. And as you saw by the solar system, we actually are kind of in the same orbital plane. Give or take a couple of degrees. But we're kind of in that same plane that we have. So it's pretty easy to understand the motion of Mercury. It's pretty easy to understand the motion of Venus. But Mars gets a little weird. And so one of the things that they were trying to explain is why, if I watch Mars in the night sky, it's going to go like this over time. And then all of a sudden, it's going to go backwards. And then eventually it comes back to going correct. And this is what is known as retrograde. So we actually observe Mars kind of does a little loop-de-loop, and life is kind of entertaining. Well, the reason is because we're closer to the sun than Mars is. So we travel a little faster. So think about this. Mars is further out here. The Earth is coming in, like on the inside of a track, right? We're coming in and we're watching Mars, and because we go around the sun faster, all of a sudden we pass Mars, and Mars looks like it's going backwards. But eventually it catches up and we get that little loop-to-loop, and that's exactly what's happening with Saturn, and what's just happened with Jupiter is we're following this little loop-de-loop because Jupiter's out here and Saturn's out here and Neptune's out here, and it just doesn't happen as often as it does with Mars. Plus, with the telescopes that they had, we could see Mercury really, really well, we could see Venus really well, we could see Mars really well, and if you've been looking at the night sky lately, Mars has been really easy to see, so has Jupiter with the naked eye. And if you really want to get some good observations, I mean, Mars has even been really, really good red color as well. If you've got a halfway decent set of binoculars, you can actually, scroll into or dive into them. Another star that's really interesting right now is Betelgeuse. Betelgeuse is the corner shoulder in Orion, and Orion is now back up, and you can see Orion in the evening sky. Betelgeuse is doing weird things. It's actually dimming. Last year it went from one of the brightest stars in the night sky to kind of like one of the 50th brightest stars in the night sky. It's a possibility that Betelgeuse is going to nova at some point in time. Or has nova, but we just haven't seen it yet. Because remember, we look at the, when you're looking at the night sky, you're looking at the past because it takes so many light years for things to get to us. So there's a lot of fun things that are happening. So first thing that we see is the retrograde. And Kepler, we'll get to this as well, but there's a reason why we go through Kepler's laws at this point. Kepler says, okay, let's look at the sun, and based on the observations by Brocchi, he concluded that all orbits around the sun are ellipses. Remember, a circle is just a special ellipse. Circle is just a special ellipse. So that's his first law. The second law is that if I look at the sweep, the time that it takes for the planet to sweep here, and the time that it takes for the planet to sweep over here, the areas of those two triangles are the same. And you just saw from Newton's notes, Newton was trying to prove this mathematically that that is the case. Kepler did it empirically using Brocchi's data and showed that that was happening. The next part was that the time that it takes to go around the sun, the period of the orbit, is proportional, I think it's t squared r cubed, don't quote me on that right now, but there's a proportionality, I just don't remember having looked it up recently, that these are proportional and we have that particular aspect. So, Newton said, that's pretty cool information. But his question was, why do the planets stay in an orbit? That was the question. And he said, could I prove that by looking at the Earth, good old Earth here, moon system. Oh, and by the way, we have another moon. Not just it's going to leave us, but we've captured a large rock in our orbit, orbiting around us right now. So we have a mini moon at the moment. That came out last year as well. But it'll leave us very much like how they slingshotted the various exploration satellites around Saturn and Jupiter and Mars. This one will leave us eventually. It'll get flown back out. But for right now, we've got 2 natural moons. But the Earth moon system. And this is where we get this idea that these two things are attracted to each other. And we're going to stay in orbit. And this is where this all comes from, in that we have these individual mass attractions here. The moon is actually pulling on the Earth, and the Earth is pulling on the moon, and it goes back and forth. And that's actually, and we know this to be the case because we have tides. We have tides. And that's what leads us to having the orbital system. And when Newton did that, he said, well, let's look at this. There is some force between the two, and it turns out it's proportional. And we use the gravitational constant, but mass 1, mass 2, divided by the distance squared, is going to equal with the force of attraction between two masses. And it turns out we can actually measure that. We can actually determine gravity, and we can actually measure it. And so one of the things that I have for you in Blackboard is the replication of the Cavendish experiment.
Good grammar and spelling are important, but if you want to write essays that inspire...
Hey folks, how you doing? We're looking for a replication on the Cavendish experiment here. So we've got our torsional balance, which is a piece of wire suspending this metal rod here with 2 weights on either side. And I've been letting this come to rest for a long period of time and doing just really fine adjustments, trying to get it perfectly still. We're then going to add weights, or add bowling balls or masses near the 2 ends of the rod and try and get that gravitational pull to cause this whole thing to twist. So first thing we need to do is establish our baseline. What kind of motion are we seeing with this thing without the interaction of the bowling balls with this? I've been letting this thing calm down all day, and it still isn't perfectly still, but it's really, really close. So I'm just going to watch for a little bit, and you guys get the benefit of high speed. I'm going to be sitting here bored as heck as I watch this little laser goes back and forth. So I got a laser here bouncing off a mirror on the rod and then falling onto the ground right here. So you can see that in the video. Looks like, yep, I think we're okay. And that's just going back and forth a little bit. I've got the meter stick to provide a point of reference so we can see the motion of this without the bowling balls. And then we'll put them in place and see if we can observe some noticeable changes. Hopefully, keep your fingers crossed. All right, so let's see how this thing goes. And get a clock in the picture too, so you can see just how dedicated I am, how much time I'm sitting here watching this little laser go back and forth a few times. I'm going to put some marks on the floor so we have a baseline mark so we can see any differences there. Well, it looks like we're not quite as steady as I was hoping. We still are seeing some shifting, so it's oscillating back and forth, but it's changing the range over which it's oscillating right now. So I think I better let this one sit for a little while and come back to it first thing tomorrow morning after it's had the whole night to settle down. Hopefully it doesn't get bumped between now and then, and we'll see if we can get some more at that point. Cross your fingers for me. Hey folks, we're back. It's the next day, and I've got this thing pretty stable, or at least it has been. I've been literally tiptoeing around the room to try and avoid moving air as much as possible. So we are looking for such a small amount of force with this, it just has to be so sensitive that even little tiny disturbances can disrupt it. I put a little paper down to make the mark easier to see, and it's graph paper, which makes it easier for me to tell when it's moving and when it's not. So I'll give you the benefit of the high speed here as I mark the current motion of the laser light here as it goes back and forth. And then once we kind of get an idea of the range of motion, hopefully fairly small range of motion, we'll put the bowling balls in place and see how that range changes over time.
Bowling balls in. There's where you put the bowling balls in.
We can get this thing to oscillate on its own without interference from me. It looks like I've already caused a little disturbance in this. Maybe the fact that we're seeing this get so far over to the right, that may actually be more a result of me just moving nearby this thing than those 2 bowling balls in place. So we'll have to watch what happens over time with this. I'm just going to let this run. You guys get the high speed.
But we can see is that the bowling balls do make a perturbation. Cavendish actually did this as a very fine experiment, but what you do have is that the two masses attract, just like the moon and the earth attract, except they're very, very large masses. And I've got this one on there. I also have a different version of the Cavendish experiment out there that you can actually look at. But what we get is that allows us
10 or 12
to be
minutes
able-
of me sitting quietly in the corner trying not to scream.
that actually gets us the mass, or the value for G. So you can actually do that and measure that value for G. And I'm going to write it out for you real quick, but I don't want to make many mistakes, so I'm going to look it up. Because I never remember it off the top of my head. It's not one that I use a lot. G is equal to 6.67 times 10 to the minus 11 Newton meters squared kilograms squared. And this is what is known as the universal gravitational constant. And it's actually measured by doing the Cavendish experiment. That's how we, that's,
G over the R squared as well?
right now, this is just G by itself.
No. On the F equals G M1.
Well, we usually write it like this,
Okay, thank you.
but it doesn't matter because this is the exact same thing.
Okay.
We just generally write it like that by convention. But mathematically, it's the same thing. So, what happens here, if I look at this force, G, mass 1, mass 2, over R squared, R is usually the distance, it is the distance between the two centers of mass. Because it turns out that this stuff is gonna work as if the center of mass. And this actually equals, if I'm doing weight, okay, this is the universal law of gravitation and this is weight. Little g works out to be the big gravitational constant, mass of the Earth, radius of the Earth squared. And if you think about that for a minute, if I'm here at the Earth, and here's the radius of the Earth, and most of what we do is right here at the edge, we're in such fine, or in so many little digits off that this actually works. Which is also why, when we measure the gravitational constant, doing free fall, it's different here than it is, say, up here, because I'm looking at my radius of my Earth here, because we're a squatty planet. We're not a perfect sphere. We're actually like a squashed basketball. This R is slightly different than that R. So you're going to get a slightly different value for gravity depending on where you are in the Earth. And then there are other changes as well. You know, if I happen to be above a pretty dense portion of the Earth, I'm also going to get that kind of an effect as well. But gravity, our acceleration due to gravity, actually can be looked at by looking at the universal gravitational constant related to the radius of the Earth. So we can do that experiment. So this is Newton's law of universal gravitation. And that tells us, and one of the things that we use that for is, we just use that to determine what gravity would be like on Jupiter, or what gravity would be like on Saturn, or what gravity is like on the moon. Because that's going to be related to the two different masses. The mass of Saturn is different than the mass of the Earth, so I'm going to get a different acceleration due to gravity on Saturn. The mass of Jupiter is different than that of the Earth, and I'm going to get a difference associated with that factor of gravity. And you guys have two examples in there, and you can actually, in our book, in the cover materials of the book, you can find the mass of the Earth and the radius of the Earth. Couple things that we do with this is not only did they do the Cavendish experiment, but I can take a mass and I have a second mass the line of action of the force is going to be between the two masses. Now if I put in a third mass, these two will be attracted, as will these two be attracted. And now I end up having to, if I'm going to do a sum of the forces, so if I want to see which direction this mass is going to go, if I want to see if this mass is going to go towards mass 2, or if it's going to go towards mass 1, or it might go off somewhere like this, I have to do this in terms of vectors. And so what I would end up doing, so let's actually set this up as a free body problem and 3 diagram problem. So we're going to put our coordinate systems here. So I've got mass 1, I have mass 2, and I've got the little teeny tiny mass here, mass 3. Because of Newton's law of gravitation, this mass is going to be attracted this direction, and it's going to be attracted that direction. And if we go ahead and put some numbers to this, we'll call this 1 meter, we'll call this 1 meter, and we'll say mass 1 is 3 times the little mass, and we'll say mass 2 is 2 times the little mass, and this is just our little mass. And we want to know what the motion of that mass is going to be. Well, first thing I got to do is calculate the force from mass 1 and mass 3. That's going to be Newton's law of gravitation. We're going to be 1 meter squared. And then I'm going to have 3 of the masses times 1 mass. So this is going to give me a magnitude of 3m squared g. It's going to be my value. And if I write that in terms of my vector notation, this is going to be minus 3m squared g in the I direction because it's attracted that way. Because we're looking at this mass. We're standing, like we're playing the Who and Whoville, and we're on a particle of dust. Very disturbing story to me. Horton Hears a Who, totally disturbing story to me. I have a couple of things that are totally disturbing to me. Horton Hears a Who. And it's the same concept And that Horton Hears a Who and the Little Who's on Whoville. We've seen it in Men in Black, the galaxy on the cat's collar, or the galaxy in the subway locker. Same concepts. So we're going to play the Little Who here, and we're going to sit there. Now this force, if we look at that force 2, 3, is going to be our G, but now I got to know what this R is. Lucky for not us, we know how to get that, right? This is C squared is equal to A squared plus B squared, because we set this up as a right triangle here. So this is going to be 1 squared plus 1 squared, so C is going to equal the square root of 2. So this is going to be G over 2 because I'm doing the square, right? So I'm doing the square because we're using this equation, F is equal to GM1 M2 over R squared. So that's a G over 2, and now I've got 2M times 1M. So this magnitude is just going to be GM squared. But I also need this angle. Now I can either use my trigonometry to find that angle, or I can use the fact that I know that this is an isosceles triangle and that this is going to be a 45-degree angle. So you can either go ahead and prove that to yourselves, or just remember from geometry that that's going to be a 45-degree angle. So now my vector for F23 is going to be a negative, because again the x direction's in the negative, it's going to be a negative GM squared in the I direction. Oops. And that's going to be cosine 45 degrees in the I direction, plus GM squared sine 45 degrees in the J direction. So now the resultant force, just like what we've been doing all along, I'm going to take force F13 plus force F23, and this now is going to be minus 3m squared G minus GM squared cosine of 45 in the I direction plus GM squared sine of 45 in the J direction. And that would be the line of motion that that mass is going to take. So in your homework, you may have a couple of problems that deal with Newton's law, universal gravitation law. And we will come back to it when we start dealing with circular motion. But our book chooses to bring it out here. And I never like to just throw out a law without telling you why we have it or where it comes from. And usually we talk about Kepler's laws when we start talking about circular motion. But I wanted you all to see where it comes from now. Okay, one other force law that we have that I never am exactly sure where they actually jump it in. But I also deal with springs. And this also comes from another buddy of Newton's. And this is Hooke. And a lot of you may have run across Hooke, because he was more of a biologist. He actually also played with light. He worked with microscopic things. And so a lot of people on the biology side know him because of his drawings of things like fleas and other small things, and he's one of the first ones that actually sketched what you could see through a microscope. So a lot of people look at Hooke. Now, why he got fascinated with the flea, I really don't know. But you gotta remember, fleas were the scourge of the earth. They actually brought us the Black Plague. It's the fleas. You know, so you have the bubonic plague spread by fleas. So he looked at how high a flea could jump. And so he actually started looking at springs and equating the leg and the leg muscles to springs. So one of the things he did was he did an experiment that looks like this. He would put different weights on the spring, and he would look at the stretch of that spring. So the stretch of the spring is going to be the change in length, which is going to be the new length minus its unstretched length. And so he was going to look at the stretch. And he knew that this was a force because I've got a weight, and that was the force being applied. And what he learned was that if I did this, I would find that the force was proportional to the stretch. And depending upon my spring, I could figure out a constant. And so he comes up with Hooke's law, and we use a negative here because this is a restoring force. The spring wants to go back to its original shape, so it's a restoring force, so it's actually a negative, and then he multiplies that by the stretch. And my spring constant is in Newton meters, and the spring constant K, is based on the material, shape, and other properties. So this spring constant has to be empirically determined. And if you've ever looked at the spring around your shock absorber on your truck, you know it's going to have a different kind of spring constant than the spring that you have in your watch. And we have lots of different things that are springs or can be equated as springs other than what we traditionally think of as a spring. A watch spring actually looks, and you guys have probably seen a watch spring. A watch spring is like a little metal piece that looks like this. It kind of curls around, and when you tighten a mechanical watch, we tighten up that spring, and as it releases is where it's going to give us our release there. A buggy spring, if you've ever seen on a horse buggy or a wagon or something like that, it'll be two pieces of metal that are like this, because this can compress back and forth. And this acted as an early shock absorber on horse-drawn buggies. If you look underneath your truck, you'll find things that look like this. I've got a piece of metal, I have another piece of metal, I've got another piece of metal, and it's bundled up and tightened together. This is called a leaf spring. I got a leaf spring in there. Another, even though we don't think about it that way, we can look at if I have molecules in solids, the interactions of those molecules act as springs, so we use it in chemistry a lot. That's how we can do IR spectroscopy. Is because we hit resonances of those springs. So understanding springs and using Hooke's law becomes very important. Now this is another interesting thing. I like talking about Hooke's law, because Hooke's law says that my force is going to equal the negative spring constant, and the force is along the line of stretch. So that's where I'm gonna get my direction. And we call it Hooke's Law. Well, it turns out from a materials property, we know a couple of things. If I have a rubber band and I apply force to a rubber band, nothing's gonna happen, then all of a sudden something happens. And as long as I don't overstress it, it'll go back to its original shape. But we also know that at some point I can overstretch it and it's gonna stay stretched. And it'll never go back to its original shape. So a rubber band will only obey Hooke's law over a certain region. It turns out we get the same thing with plastics and metal and all kinds of things that if this is a way that we do tensile strength and test metals and test products, that I could pull with a force here and I could pull with a force there, and as long as I don't deform my metal, it's going to behave, it'll have a region that looks like Hooke's Law. And in fact, what we do see, and we can do these plots, is usually what will happen is we obey Hooke's Law, and then we do something weird, and then we break. And we have a lot of these force tension diagrams based on material. But we call this Hooke's Law, but it's only going to obey over a certain region of materials. It's only going to work for a certain region in a physical sense as we go through stuff. But this is another force that we have to deal with. So now when we're looking at what we have in terms of forces, we have Newton's second law in the form that we're going to use most of the time. This is going to give me my sum of my forces is going to equal my net force, which is going to be equal to the mass times my acceleration. I've got Newton's law of universal gravitation. And I have Hooke's law. And we started talking about it because we actually showed, and I did a little demonstration under the document camera, that until I raise up my inclined plane to a point, there's a force that's holding this up, and we call that the force due to friction. And the force due to friction is going to equal the coefficient of friction times the normal force. So this is the normal force, and this is the coefficient of friction. And the coefficient of friction is dependent upon material, and there's two of them. One is the coefficient of static friction, and one is the coefficient of kinetic friction. And if you look in your book, you'll find tables of these things. And you'll also find that the coefficient of static friction is greater than the coefficient of kinetic friction. So depending on what I have, steel on steel, wood on wood, wood with sandpaper, wet snow, dry snow, and usually one of two things are happening when we're working the problem. First thing is they usually will give you the coefficient of frictions that you're going to work with. Or you're going to be using the forces to determine the coefficients of friction. So those are the things that are going to come into play. So right now, if I were putting my little handy dandy what I need to have together to do my homework problems, this is going to be my easy sheet to get there. And if you look at the summary of your chapter, it's going to give you Newton's laws of motion. We've got the normal and kinetic friction forces, and we've got static forces and applications of Newton's laws. So we've got some things in there, and I may have given you Hooke's law a little early, but at least you've got it there to start working with. All right, so we ready to work a couple of problems? Now that we got the theory out of the way. Okay, so we'll start with a simple one. All right. So we are told you want to go ahead and hit the light so people can take notes. 10 newtons, and this is going to be in the x direction. Is applied to a mass of 5 kilograms on an ice rink. So right now we're going to assume no friction. We want to find the acceleration on the block. The first thing we do is read the problem. Then the next thing we do is we draw our force diagram. So we do know that we have a force that's acting, that's our force due to gravity. We may not have to use it, but we'll go ahead and put it in there. That's going to be the weight on the block, and if I want to calculate that out, that's going to be 5 grams times 9.81 meters per second squared, and I can calculate that out. It's going to give me 49.0 newtons. We're told that we're going to apply a force, okay, and we're told that that force applied was 10 newtons. We know that the force in the x direction is going to be the mass times my acceleration in the x direction. I'm going to solve for acceleration because that's what I was asked for. And that's going to be my 10 newtons divided by my 5 kilograms. So it's going to go off at 2 meters per second squared. Okay. Oh, since it's football season, we can do a football problem. We have a football player accelerates from rest to 10 meters per second in 0.5 seconds if the player is 90 kilograms. What force does he hit the opposing player? So we know we're going to use force is equal to mass times my acceleration. I need acceleration. And some of you might say, I don't have enough information, but yeah, you do. We know that the initial velocity is equal to 0. We know the final velocity is 10 meters per second. We know the time is 0.5 seconds. I've got 3 equations of motion that are possible. I have v squared is equal to v naught squared plus 2a change in distance. Can't use that one because I got change in distance, no time. I've got my change in position is equal to v naught times time plus 1/2 at squared. Well, that's good, I got time this time, but I don't have a change in position, so I can't use that one. But I got the last one, which is my initial, or my final velocity is equal to my initial velocity plus my acceleration times time. Ooh, I got both velocities. I have my time, I can use that equation to solve it. So it's going to be v final minus v initial divided by time is going to equal my acceleration. So I'm going to get my 10 minus 0 divided by my 0.5 seconds. So this is in meters per second. This is in seconds, so I'm in the right units. And that gives me 20 meters per second squared. Force is going to equal my 20 meters per second squared times my mass, which was 90 kilograms. This is going to be 1,800 newtons, which is why football players wear pads. And that is actually reasonable because we're not asking our football player to sustain that acceleration for very long. Okay. We have a bag of sugar, and I'm using an old bag of sugar. No, I guess I only changed the 5-pound bag to the 4-pound bag. Yeah, that weighs 10 pounds on Earth. We want to know what it weighs on the moon. Well, we're told that gravity on the moon is 1/6 of gravity on Earth. Okay? We happen to know that gravity on Earth is 32 feet per second squared because I'm in pounds. I need to be in feet per second squared. Pounds are a force. Remember that mass in the English system are slugs. So basically, in this, if the weight on Earth is going to be the mass of the sugar times acceleration on Earth, that's going to give me my weight, and we know that that's 10 pounds. Now I'm going to do the mass of the sugar is the same. It's not going to change anything. So I can calculate that. So that's going to be 10 pounds divided by gravity, which is 32 feet per second squared. And if I do that, there's 10 divided by 32. There's lots of ways to approach this problem, so this is just one way. Let's just start over. 10 divided by 32. This gives me 0.3125 slugs. And now I'm going to do mass times gravity on the moon, which is going to be mass times gravity on the earth, divided by 6. So we didn't necessarily have to do that, but it's just a fun way to show you what you get if you do that. And so this is just going to be my 10 pounds divided by 6. And if I do that, 10 divided by 6, it gives me 1.67 pounds. Friction problem real quick. Okay, so we've got an inclined plane. And I've got a box on my inclined plane. And we're told that the box is going to start to slip at 33 degrees. We're told that the box has a mass of 10 kilograms. And we want to find the coefficient of static friction. So we want to find that. All right, so here's a couple of tricks here. When I have a box like that, we know that I'm going to have the force due to gravity going down. I have a normal force going up. Using Newton's third law, there's an equal but opposite force over here. That's equal but opposite the normal force. And I like to call this force perpendicular to my plane. Because the motion that's going to ultimately happen here is it's going to go down along the plane, and this is my force parallel. There is a geometric argument that shows that this angle is equal to that angle. So if this is 33 degrees, that's 33 degrees. So my force parallel is going to equal, because if this is mg, this side is going to be mg sine of my angle, where that angle is this angle right here. But my geometric identity says that those two angles are equal. So my force parallel is going to be mg sine of the angle. My force perpendicular is going to be mg cosine of the angle. So what we've been doing out of habit all the time so far, you want to be careful when we're dealing with this inclined plane. You want to be very careful, because you're going to get yourself a little discombobulated and confused, and you'll switch your angles and it'll cause you to get the wrong answer. So when it starts to slip, and this is a key thing when you read it in your problem, when it starts to slip, it hasn't quite moved yet. And when it hasn't quite moved yet, this tells us that my acceleration is equal to 0. So I'm going to do the sum of the forces parallel. That's going to be the force down the plane minus the force due to friction that's resisting the motion. is going to equal 0. Force down the plane is going to be my mg sine theta. This is going to be, so I can add it, do it up. It's going to be my static friction times the normal force. And that's got to equal 0. Now, my forces, some of the forces perpendicular, I don't have any acceleration perpendicular, so again, I still don't have an acceleration, so mass times acceleration is equal to 0. But I have the normal force pointing up, and I have the equal but opposite pointing down, and I've got the mg cosine of theta. So now I can solve, this is again 2 equations, 2 unknowns, and I can solve for the normal force. Normal force is mg cosine theta. So now I've got minus mg sine theta is equal to, or minus, or plus mu s mg cosine theta is equal to 0. So I get mu s mg cosine theta is equal to mg sine theta. Mu s is equal to mg sine theta divided by mg cosine theta. mg's cancel out. I didn't need the mass of the block. It was extra. This is tangent of the angle. We know the angle is 33 degrees. So my static friction is 0.649. And in this case, it will not have units because the coefficients of friction don't have units. This is a ratio, and that's how those actually calculate out. Okay, I'm going to stop there, because I really don't have enough time before we lose everybody. And then we will start back on Wednesday.